Welcome to the final lesson for Chem 105. If you're studying to become a safety inspector, you may not study much more about fire. For firefighters, hopefully this will be a review or a brief introduction to some of the other topics we understand. So some basics. Definition of a fire is a rapid oxidation reduction reaction. And remember before talking about oxidation oxidation is the taking of electrons and reduction is the giving of electrons. And so carbon is oxidized to form carbon dioxide, and hydrocarbons are oxidized to form carbon dioxide and water. But oxygen is not the only oxidizer. Chlorine gas, for instance, sodium metal will burn in chlorine gas to form sodium chloride salt. So it's not just oxygen that can cause fires. There are fires available from other oxidizers. We're going to talk about the different fire theories. There's a fire triangle, fire tetrahedron, and the life cycle of fire theory. And we're going to go through these, and the idea is that if you remove one of the pieces from the triangle, the tetrahedron, you put out a fire. Or if you interrupt one of the stages in the life cycle of a fire, then the fire will go out. Starting with the fire triangle, this is in kind of the older one, you need three things: fuel, heat, and oxygen. And so fuel is anything that's going to burn, and oxygen is usually oxygen gas, could be any oxidizer, and heat is a source of power. For instance, wood, so if I have a block of wood, there's oxygen and there's fuel, but wood is not going to burn unless there's heat available. And remove any of the side of this, and the fire will go out. So kind of like if you go camping, you have a campfire. One of the ways you can put out your fire is you throw water on the fire. How does that work? Well, the water takes away the heat, and then the fire goes out. Tetrahedron is the same as the fire triangle, except there is the chain reaction. The chain reaction allows the fire to propagate, and so the free radicals there are needed, and certain fire agents like halons and carbon tetrachloride can prevent these radicals. Another application of this is actually in our stealth technology. So our stealth jets, they contain a compound called sulfur hexafluoride. They added the fuel. Sulfur hexafluoride is a free radical scavenger, and that reduces the heat signature of our jets. So actually, part of this is also part of our stealth technology for our military. Life cycle theory. Here is the life cycle theory. I'll go over the general, what each stage means. But the implied thing, the input heat will raise the fuel up to its ignition temperature. Then this fuel will spontaneously mix with oxygen, which will then cause collisions, which will further on keep on going, cause more ignition, which will cause the fire to keep on going. So the idea of the life cycle theory of the fire is that this is spontaneous and natural. And when one puts out the fire, you have to interrupt one of these steps. If one of these steps is interrupted, the fire will go out. So input heat, this is required to vaporize the fuel to reach the ignition temperature, which we'll talk about later. The fuel needs there to burn, and at oxygen, so this is atmospheric, not contain the fuel like gasoline has ethanol and some ethers in it, for instance, that have oxygen in them, but we don't count those in this theory. We only care about the oxygen in the air. Proportioning, this causes molecular collisions, so increase in the temperature causes more collision. Also, backdrafts are explained by more oxygen coming in, so more proportioning to the life cycle theory. Mixing goes to the flammable range, which we'll talk about later, because sometimes there's too poor of a mixture or too rich of a mixture that will not allow a flame to happen. And then the continuity, the heat is rated back to the fuel and continues the cycle. So let's interrupt. If we interrupt any one of those steps, the fire will go out. Some definitions. Vapor pressure. This is the pressure exerted by the vapor of the size of the container at equilibrium. This is also the boiling point of the liquid at a certain temperature. So if the vapor pressure is 25 torr, if the ambient pressure was 25 torr, that liquid would boil. So you can boil liquids by reducing the pressure, and at that point that the liquid boils is the vapor pressure. That's another way to look at it. Liquid is anything that has a vapor pressure not higher than 40 pounds per square inch absolute. A is absolute, not gauge, because absolute includes the 1 atmosphere pressure from the atmosphere, or whatever the external pressure is. Boiling point, this is when the vapor pressure equals the atmospheric pressure. For here on Earth, it usually means 1 atmosphere pressure, so we call the boiling point of water 100 degrees Celsius. That's when the vapor pressure of water equals 1 atmosphere of pressure. A flash point, this is the minimum temperature that a liquid will give vapors sufficient to form an ignitable flame with air near the surface. So if you have a temperature and you hold a match up, it's the temperature that you'll see a flash of fire. Flammable liquid, this is anything that has a flash point below 100 degrees Fahrenheit. So these are really able to burn easily. Combustible liquid, this is something that's a flash point above. So the difference between flammable and combustible, 100 degrees Fahrenheit. Ignitable mixture, this is the mixture of fuel and air or oxygen, because air is only 20% oxygen, within this flammable range that you can keep a flame, a propagated flame that will keep on burning, and after the ignition source, so a spark, after the thing starts going, what a flame will keep on going. The flammable range, there's an upper limit and a lower limit that things will burn. The flammable range is that range that will burn. So we have the lower explosive limit. This is the minimum concentration that you will not be able to ignite the vapor. So if it's below the lower explosive limit, there will not be an explosion. One can be above the upper explosive limit. The mixture is too rich, so there's not enough oxygen there to be able to cause an explosive or explosive situation. So there's a range here. You can be too weak, and there can be too much, so too lean or too rich. And in the middle, though, there can be an explosive event. Keep on going with definitions. Lots of definitions here. Ignition temperature. This is the lowest temperature in which a material must be raised to initiate or cause a self-sustained combustion. The auto-ignition temperature. This is also how diesel engines work, actually. Diesel fuel will be compressed down to its ignition temperature, auto-ignition temperature. Specific gravity, another definition. This is the weight of solid divided by the weight of water. So specific gravity is dimensionless, but it's in grams per cubic centimeter or grams per milliliter. Vapor density, this is the relative density compared to air. Air equals 1, so it's kind of like specific gravity, but it's compared to air. Heat of combustion, this is how much energy fuel releases. So compare something like paper, like solids. They burn at about 6,000 to 7,000 BTUs. BTU is a British thermal unit. That's the amount of energy it takes to raise 1 pound of water up 1 degree Fahrenheit. That's what a BTU is. A calorie is the amount of heat required to raise 1 gram of water up 1 degree Celsius, or a kilocalorie or a nutritional calorie is 1 kilogram of water 1 degree Celsius. A joule is a Newton meter, and 4.18 joules equals a calorie. So if you want to know the difference between all these temperature units. Flammable liquids and flammable gases, they release more heat than flammable solids. In general, heat, this is the vibration of a group of molecules. So temperature is the average kinetic energy. So temperature says how fast things are going. Heat, you feel it in the form of infrared radiation. Infrared radiation causes things to vibrate. So that's why heat means the total amount of vibration. It's a stored energy. Temperature, just talked about that, average kinetic energy. So problems with flammable liquids. Some produce vapors that are flammable. So the gasoline, for instance, has flammable vapors. These can also be corrosive, oxidizing, toxic, narcotic, or unstable. So many people have seen that oxidizing can burn or hurt your nasal passages. Toxic, you sniff fuels enough, it will get you eventually. A narcotic, so certain people, when you breathe them enough, I've done this, like, not intentionally, but I've accidentally inhaled too much and felt a little high from it. Slop over. This is when water is trapped at the bottom of some storage tanks, and as it heats, the water will boil or expand, and then this will cause slop over, or this stuff will the oils will start to literally slop over the tank. And for you firefighters, I was told specifically to put this in there. Do not enter the secondary containment area. So if there's slop over, there's a secondary containment area, right? There's going to be like concrete structures. Do not enter that secondary containment area. That is very dangerous. So how do we get rid of these flammable liquids? So water, for low flash point flammable liquids like gasoline, water is not effective. That's not a good way to get rid of these types of fires. But for high flash points, you can use water. Foams, you can use foams for them. The choice are AFFF, or aqueous film forming foam, ATF, an alcohol type foam, or a fluoroprotein. These are used specifically in subsurface injection systems, and this resists fuel degradation. So that's an important thing about the fluoroprotein. Also, free radical quenchants. This is with the fire tetrahedron to get rid of the chain reaction. Dry chemical sodium bicarbonate, that's also baking soda, potassium bicarbonate, monoammonium phosphate, and some halogenated gases like halon and halotron. Surface application, we can fix systems, monitor portable models, elevated platforms, and again, do not enter secondary containment area. When there's a fire somewhere and there's a secondary containment area, do not enter it. So if you can learn one thing from this lesson, do not enter a secondary containment area. And if you're wondering what that means, if you go to an area that has a tank, and that tank, like a tank is a big vessel, if that vessel is on fire and there is a hazard there, do not enter the secondary containment area. It's going to be like a concrete structure around it. Do not go in it. Inject things subsurface, like fluoroprotein for a fire underground, or other large storage facilities. So as we learned from the life cycle theory of fire, and also the fire triangle and tetrahedron, heat. So you need heat to have a fire. So let's talk about how heat is transferred. One is convection. Many people hear hot air rises. That's not true. It's actually cold air sinks. So when air heats up, the air expands, which makes it lighter, and the heavier, cooler air by gravity falls down and pushes the warm air out of the way. And these, by collision, molecular collision, can go to other surfaces. So this hot air can go to, if you have a fire in the middle of your room, and then the hot air goes to the side of the room, it can catch the air on fire. And this can cause a thermal column, and that will add more oxygen to the equation, and that causes the fire to propagate as well. Heat can also be transferred by conduction. So this is like taking a metal spoon and putting it into a pot of boiling soup. If you hold on to the spoon, the heat will conduct along the metal spoon. And this causes molecules to vibrate up against each other. Remember, heat is vibration. The molecules vibrate and then making them move faster. And radiation is final one. It giving off infrared light. The infrared light will cause other molecules to vibrate, and then that causes things to heat up. So liquids can heat up by infrared light and might make them vaporize, and this can also add more fuel to a fire. Different fire classes, there's A, B, C, and D, and we give a special class to K. A is combustible solids, B is combustible liquids or gases, and K is a subcategory. Some people include it. It involves cooking oil fires, so like the people that cook their turkeys in oil for Thanksgiving. Electrical fires is class C. So this can include class A or B, but if electricity is also involved, class C. Class D are metal fires, like magnesium. So the tire, the rims on your tires in your cars, those have magnesium, and those will burn. That's a Class D fire. Class A fire, combustions. So if there's incomplete combustion, though, we'll talk a little bit more about that later, that can lead to backdrafts. So maybe you were taught this in grade school and kindergarten. If the door handle is hot, don't open your door, because if you open the door, suddenly you have heat, you have fuel, and you have a rush of oxygen that can cause a phenomenon called a backdraft and cause a big explosion. Water is effective for Class A fires. Takes away the heat is how it puts it out. Class B, liquids and gases, and generally speaking, the lower the molecular weight, the more combustible the gas is, in general. Carbon dioxide and foam, you can extinguish them with this. BLEVE stands for boiling liquid expanding vapor explosion. If you have a liquid on fire and the fire progresses, and the lower vapor pressure gases will burn first. But then as they give off heat, they're giving off all those BTUs. That heat will eventually vaporize the rest of the fuel, and then a huge explosion can happen. That's the BLEVE. A Class C fire, this is an electrical fire. A Class C fire is one that you do not want to use water to put out. Why not use water? Well, because then it can conduct electricity, and some firefighters could be electrocuted. Use carbon dioxide to put out, or something else like a halon to put out this fire. Class D fire, this is a metal fire. Do not use water or carbon dioxide, because these can be used as fuel for metal fires. So graphite is a common extinguishment for metal fires. So we talked about backdrafts. This is where it comes from. Complete combustion. If there's enough oxygen, we'll have total oxidation and will form carbon dioxide. With incomplete combustion, not enough oxygen is present, and carbon monoxide can form. Carbon monoxide is very toxic. It will cause rapid suffocation. And other oxidation products are possible. These can also be hazardous. And pyrolysis, so this is fire and breakdown. If you wondered how we get liquid smoke for cooking, you do it by pyrolysis of wood. You take a block of wood and you heat it up, and it pyrolyzes, and you purify that pyrolyzed product, and one of the products you get from it is liquid smoke. But if this is happening in a fire, you can get pyrolysis, and you can get other things that come from the pyrolyzed solids, and some of these are toxic. And so the hazards: a backdraft, a flashover. We already talked about backdraft. Flashover. This can cause so the fuels around, so they can ignite. And crown fires. These can cause trees to eventually explode. The kind of tree I've always wanted to see this. Apparently, eucalyptus trees, they tend to do this. So eucalyptus trees will detonate in a forest fire. I think that'd be kind of neat to see. Other fire gases, nitrogen compounds can be formed. So nitrogen dioxide. This can cause respiratory stress. So it'll burn when you breathe it, and may even cause hemorrhaging. Car exhaust have some. It's formed from air. Nitrogen is in fuels, can also produce hydrocyanic acid, hydrogen cyanide. That's very toxic, and ammonia. Some toxic. So halogens. So halogens are chlorine, fluorine, chlorine, bromine, iodine. So especially chlorine. This can form strong acids like PVC, polyvinyl chloride. Can form HCl. Can also form chlorine gas. Can form phosgene, COCl2. That is a chemical weapon. That is a neurotoxin. That's really, really nasty stuff. Sulfur can produce sulfur dioxide and hydrogen sulfide. Those are really smelly, and they're also toxic. In the collisions of different gases and fuel can form some complex hydrocarbons. And these form randomly. When things burn, weird stuff can start to happen. And many of these are toxic and cancer-causing. So things like benzene or naphthalene, for instance, can form. These are also fuels. They'll burn. So you're adding fuel to the fire there. So that's one of the problems with gases coming from fire. And I'm going to close this talk by talking about matches and something that's a little more at home that you're used to. So we'll talk about the safety matches and strike anywhere matches. Starting with strike anywhere matches, they contain tetraphosphorus trisulfide, sulfur, and lead oxide, lead 4 oxide, and they're on a piece of wood. And the idea is the friction will ignite. So when you strike anywhere, the friction will ignite the tetraphosphorus trisulfide, and that will burn with oxygen in the air to form phosphorus oxide and sulfur dioxide. Then the sulfur burns, and oxygen is also further provided by the lead oxide. So the lead oxide is a source of oxygen for a strike anywhere match. A safety match, you have a little piece of cardboard. I guess it often looks more pressed and has wax present, potassium chlorate, and diantimony trisulfide. And so the strike surface on the back of the pack of the matches, that has red phosphorus in powdered glass. And so the surface, you rub it, you create friction. This it will ignite some sulfur and the potassium chlorate to form potassium chloride and sulfur dioxide. And the energy from that also causes the antimony sulfide to react further. And so those are how safety matches work. And you can see that you need the red phosphorus and powdered glass to initiate the reaction. Unlike strike anywhere matches, they don't need this, but the safety matches do. And so concludes our lessons here. I hope you do well in the upcoming tests.